Okay, thank you. So what I'm going to focus on today is the FUV lunar signatures of lunar swirls. And lunar swirls, as we have heard about, are distributed around the globe of the moon. They're associated with areas of magnetized crust, magnetic anomalies. And from visible and near-infrared wavelengths, we know that they exhibit signatures similar to immature regions, as if they're relatively unweathered. Possible causes include a standoff of the solar wind, like they're shielded from the solar wind, making them making them less weathered, and so that would make them appear less mature, because it would inhibit nanophase iron production, except via any micrometeoroid or other weathering processes. And maybe it could even enhance weathering in surrounding regions, as has been shown by Kramer. An alternate explanation is dust transport caused by induced electric fields, which would mean that there would be an accumulation of especially fine-grained, especially feldspathic particles in those visibly bright swirl regions. So here what we're going to do, I talked about visible near-infrared characteristics. We're going to focus on UV, especially far UV. So these are LAMP measurements from LRO. LAMP is the Lyman Alpha Mapping Project, nadir pointed, usually looking at the surface, often taking data on the day side. So those are the measurements that we're talking about here. It's a far UV spectrograph. So the entire pass band is 57 to about 196 nanometers. Here we're going to focus on about 130 to about 190 nanometers. The really neat thing about looking in the far UV on the moon is that we are in the surface scattering regime. Our photons do not penetrate very deep into the grain. We're not talking about volume scattering, we're talking about surface scattering, where the reflectance that's measured is proportional to the Fresnel reflectance. And so we're directly proportional to the optical constant N and K of the materials that we're observing. So it's a fantastic region in which to look at the effects of space weathering. Okay. So swirls, as I said, are found all over the surface of the moon. Here's a little map from Kramer. In the LAMP data, we have looked at a few of them so far, and in this presentation, I'm going to focus on the swirl at Reiner Gamma in a Mare region and Gerasimovich in a Highlands region. Now, what I'm going to show you are some images, and they're going to be ratio images. And so I want to orient you to what we're seeing in the spectra in the far UV. These are some sample LAMP spectra. This is 120 to 200 nanometers. And the colors are not really that obvious in this projector here, but what I'm showing you is a region of immature highlands. So it's a bright ray, mature highlands, and a Mare region. And you can see that all three of them are pretty blue in this region here. The moon is pretty blue in the far UV, and we've known that since the 70s from IUE. But what you can see is that immature highlands are less blue than mature highlands, and the Mare are the most blue around the moon, and that's just a natural consequence of the more enhancement of opaques in the Mare region. Okay, so when I show you ratio images, I'm going to show you longer wavelengths out here, ratioed to shorter wavelengths. And here's Reiner Gamma. So here's a visible image. Everybody, I think, recognizes Reiner Gamma. Here is the FUV image, ratio image of the same region. Okay, this is summing up 22 months of data, doing a little phase constraint correction, and you can see that we see this familiar shape here as being relatively bright, which means that it has higher ratios, brighter at longer wavelengths than at shorter wavelengths in the FUV. So you can see here, if I overplot them, that you can, I mean, it's lower resolution, but you can certainly see a correlation there. Here are some spectra from that Reiner region. We've picked some off-swirl regions and some on-swirl regions. Let's see, here's our off-swirl regions here, which, again, sorry that the colors didn't turn out so great here, but those off-swirl regions are more blue than the on-swirl regions. Okay, the on-swirl regions here are chosen from areas that are visibly bright and have redder FUV ratios, and they are pretty spectrally flat here. I didn't do any normalizing of spectra here. They're all about the same order of magnitude brightness, but they have different spectral shapes. So the visibly bright swirl region is less blue in the FUV than the surrounding terrain. Let's look at Gerasimovich. Visible image, FUV image. Again, this is actually more data. Remember, this isn't a highlands region, so the color bar here is different. The color scale is different. Here I'm circling kind of the brightest of the swirl regions here just to help guide the eye, since it's not quite as obvious as Reiner. And we see, again, higher FUV ratios where the regions are visibly bright. Here are spectra. This is where it gets really interesting. Some spectra of some off-swirl regions here. Again, what you can see here is that they're kind of pretty flat out here, and then they start to turn up at maybe 160 nanometers, become very blue. The on-swirl regions from Gerasimovich are from right here and right here, and they're dramatically different. Okay, they are actually red, not just less blue than the non-swirl regions. So that's really different. So in general, we know from lab measurements of some lunar-like species that the blueness of the moon in the FUV can be explained by species like some pyroxenes are pretty blue. Ilmenite is pretty blue, at least in part of the region here. The reddish shape that we see in the Gerasimovich swirl looks similar to what we see in some feldspars here, with a turn up here, a red slope longward of about 160 nanometers. Okay, but there's also a link to weathering. Okay, as we heard this morning from Larry Taylor, the VNIR effects of weathering are quite well understood, quite well known, that the surface becomes darker, redder, and the absorption bands become diminished. In the UV, and this is both in the near UV and deeper into the far UV, lunar soils are bluer than ground-up lunar rocks. Okay, so this is a connection to weathering. Here's an example of lunar soils in the solid lines compared to lunar rocks with the little diamonds, and this is in the far UV. So these are spectra that were normalized out at 570 nanometers, but you can see that the soils are bluer and therefore a little brighter relative to the ground-up lunar rocks. Okay, this is linked to weathering. Here's an example of this on the moon from LAMP. Here's an image, again, a FUV ratio image of Oriental, where we can see that the bright ray adjacent to the basin is relatively red, whereas the mare in the interior of the basin is relatively blue. Note here that this red slope has a slope of about 1, so it's still not really red, but it's less blue than the mare region interior. Okay, so that first FUV weathering effect was that things get bluer. Second FUV weathering effect is that things get brighter. And this is an interesting thing that came out of the LAMP data, not from the lab data. Here's an example of a single mature highlands region compared to an immature highlands region. These are all at about the same phase angles. So about 15 to 25 degrees phase for all these different spectra, and about 20 to 35 degrees phase here for these spectra. So overlapping phase angle ranges. And the mature regions, as we already talked about, are bluer than the immature regions, but they're also brighter. The immature regions are actually darker than the mature regions. And this is something that we are continuing to study, but we're attributing it to either a lack of nanophase iron, since the nanophase iron is opaque and going to brighten surfaces, and or especially since we don't see this in the lab, a lack of gardening and some sort of compaction effect. Okay. So here we are comparing our immature highlands region in cyan. Here I had to scale it up. To our mature highlands region here in blue, and a non-swirl region, and our Gerasimovich swirls. So the point here is that swirls are not just immature, unweathered regions in the FUV. They don't look like immature regions. They are brighter than immature regions, but also a lot spectrally redder. So two differences. The swirl regions actually look pretty similar. I already mentioned to like a feldspar, but it's more similar to a somewhat weathered feldspar. It's not a fresh feldspar. And we've done models similar to what Hapke has done, where you can add inclusions of nanophase iron. And what happens to the feldspar is that out in this transparent region here, the albedo drops. And so we think that the Gerasimovich swirl is something similar to a somewhat weathered feldspar. So I'm going to summarize here. These are small words here, but I'm going to try to step through them if I have time. We see the swirls in the LAMP FUV data. They're spectrally red compared to the surrounding terrains. We think that they are actually weathered to a certain extent because they're spectrally different from immature regions, because the immature regions are darker. But they don't show the spectral evidence of being mature because they're not spectrally blue in the FUV. Immature soils, such as bright rays, are dark in the FUV due to a relative lack of nanophase iron, or perhaps a lack of gardening, a different compaction effect. And spectrally, they're a little blue, probably due to some amount of pyroxene. Mature soils are relatively bright compared to the immature soils, again, probably due to nanophase iron or gardening, and are bluer than the immature soils, okay? Maybe because they've got weather-produced grain rims that have increased abundances of ilmenite. So swirls are relatively bright like mature soils, but they're spectrally red and not blue. So it's spectrally consistent with a moderately weathered feldspar. And so this is actually consistent with the dust transport and compositional sorting model of Garrick Bethel, but we may prefer that the characteristics are consistent with the model where these magnetically anomalous swirls stand off a lot of the solar wind, which would inhibit a bluing of the spectrum, but they are prone to weathering by micrometeoroids and maybe other processes, as we heard this morning, which would act to weather the soils. And so this gives us a clue to distinguish the effects of weathering from a couple of different types of processes. And we're going to be working more on that in a future paper here. And I'll also mention that the more data we get from LRO, the better, so go LRO. Thank you.
Please introduce yourself. Tim Glotch, Stony Brook University. This is really cool, and it's a neat thing I hadn't really seen much of before. But I just wanted to make sure I was clear on one thing. The Reiner gamma swirl spectra, would you characterize those in your own words as red or just less blue?
Less blue.
So it's really just the Gerasimovich that is
so
far at least. Yeah.
The most dramatic effect.
So I think it'll be really interesting to see more of these characterized and see if there's kind of a trend, and that's kind of what we're doing through Viner data right now is seeing where things fall on and off these types of weathering trends that we've observed before, and I think that something similar here in the UV is going to end up being really interesting.
Yeah, really interesting, and clearly kind of host composition has something to do with it too. So.
Yeah, hi, Carl Hibbs, APL. So just want to follow up on Tim's question, understand the characteristics of this. So are you saying that swirls are generally redder than the non-swirl terrain that they're in? Reiner gamma is actually red, whereas
less blue, I'd say.
Gerasimo.
Less blue.
The highland stuff, that's the swirls in the highland area is red. Swirls in Mari is just less blue. Mm-hmm. Yeah, do you understand why weathering though would actually cause materials to be brighter? Wait, space weathering, yeah. Then an unweathered material is darker in the far UV.
Well, a couple of things here. I'm gonna not be blinded. remember, we're in the surface scattering regime, so the presence of opaques are going to help to relatively brighten materials.
Okay.
So that's got to be related to that.
Can you speak to the microphone?
I'll go one.
Sorry.
So it's got to be related to the presence of opaques, probably in weather-produced grain rims. But also, and I'm just, this is something that we're still working on here, but because we don't see it so far in the lab, at least in the few samples that were measured by Wagner of ground-up lunar rocks versus lunar soils, that maybe it has something to do with actually the native characteristics of the moon and the compaction and the amount of scattering between particles and the grain size.
Yeah, I was vaguely wondering if there could be scattering effect. It says the surface effect, it may be quasi-specular reflection causing the increased brightness, what you're implying, right? Do the higher increase in the imaginary index of refraction may be leading to that. So what you're basically saying, maybe
I'm just saying that it could be compositionally related from weather rims and or something about perhaps interparticle scattering due to fluffiness.
Yeah, I like that. Thanks.
So it's a quick question. One last one. Michael Poston, Caltech. Amanda, have you considered the rates of the weathering in the lab? Like,
no, not yet.
Is the rate of bluing and the rate of higher albedo, do they go at the same rate, or could they be used together to get an age, perhaps?
Well, we haven't gotten into this too much, but since the immature soils are kind of blue, but not as blue as mature soils, but just aren't as dark, then that might say something about the rate of the different processes. So we'll be studying them.